go. So we now have V is equal to M over D, and the last thing we need to do is we need to have V on the left, but guess what? That's already there, so we're good with that one. That would allow you then to say, if you had values, you could then plug them in. You could say, oh, I know that this substance has a mass of 13 grams per 130 milliliters, and then I could do my math and get my answer of 0.10 grams per milliliter. Okay, so it allows us to make a nice sentence structure, you know, a mathematical sentence that goes left to right. Okay. What if we wanted to solve for M? Equals M over V, and that's going to be V times D, because we can take the V and move it up. So now we have V times D equals M. And the last thing we need to do is get the M on the left. What can you do if M is on the right and the other stuff's on the left? Just switch the whole thing, right? Just flip the whole thing. So you can then say M is equal to V times D. And that would allow you then to say, let's say you had some numbers from a question, that would let you say, I have 10 milliliters times 27 grams per milliliter, because remember we just found out that the units of density could be grams per milliliter or kilograms per liter or any mass over any volume. And look what happens here. What happens if you have 3 times 2 over 3? What do those 3's do to one another? They cancel each other out. So if you have milliliters on the top and milliliters on the bottom, what do they also do? They also cancel each other out. And what unit are we left with? Grams. And isn't that brilliant? What unit did we want? We wanted grams because mass is measured in grams. So anytime you do a problem, your units should all work themselves out, so you end up with the unit of the thing you were solving for. Okay, so that would be 270 grams. Okay, so there we go. That's how we would do one. Would you like to see another example? Yes, we'll do one more. If you are like, I don't need one more, then you can go ahead and get started on pages 127 to 129. Okay, but I will do another one because some people were away last week or might need a little more review. Okay, so we have I. I stands for current. And I is equal to Q over T. Now, you should know what T is. What does T stand for? T stands for time. And Q is that one that we just added in on our table up here. You can look it up. Q stands for charge, and it is measured in coulombs, and the unit is C. Okay? Oh, should be over here. There we go. So if I wanted the unit for I, which is current, I need to take the unit for charge and divide it by the unit for time. So Q is measured in coulombs, and time is measured in seconds. So we have coulombs per second. And I wrote out the whole word there because those might not be familiar words for you, especially Coulomb. But normally we would just write C over S, coulombs per second. Anyone remember their grade 9 electricity unit? Anyone know what a coulomb per second is? Or another unit for current? That right there, that combination of units is actually an ampere or an amp. You remember learning amps? You measured them? Okay, so that's an amp and its abbreviation is A. But the real unit is coulombs per second, but we don't always want to write out coulombs per second, so we can write out amps. Do you need to know amps? No, no you do not. But you should know that sometimes when we write a unit, there's other units hiding inside it, right? It can be, we're just writing a simplified form. Solving our problem here, if we wanted to solve for T, first thing we want is we want T on the top, we want T by itself, and we want T on the left. So we have I equals Q over T. Is T on the top? No. We can bring it to the top by moving it up to the other side, because right now it's on the bottom. If we move it to the other side and put it on the top, now it'll be on the top. So now we have T times I equals Q. So T is on the top. T is not by itself. So I can take the I and I can move it down to the bottom. So now we have Q is going to be over top of the I. So T stays where it is, Q stays where it is. The only thing that's moving is the I. So T is by itself, and then T is on the left. Okay. And last but not least, we're going to solve for Q. Okay, so we have T is equal to Q over I. Oh, Q on the top. Hey, we don't have to do that. Yay. That's nice. Is Q by itself? No, there's an I here. So we need to get rid of that I so we can move it to the other side, but when we do that, we need to move it from the bottom to the top. And so now we will have I times T equals Q. So we have Q is by itself now. And then finally, we need Q on the left. Just take that whole equation and flip it. Q is equal to I times T. Okie dokie. And I would like to give you guys some time to just practice on pages 127, 128, and 129. Okay. And I'll also put down what your homework will be, so if you finish early, you can get started on that. Yes? You have a question, and I'll be over in just 1 second. Okay, so if you finish, you can work on which video? I think you're right, and I'm trying to remember what it was. Oh, studying methods. Do we want to watch the study method right now? You're curious, okay. So let us go to our teams. And we will go to study techniques. Okay, and here's one. This one doesn't have a video, but I think it's really important. Put your phone away for better grades. And if you don't believe me, then you might believe the University of Texas, who has done a peer-reviewed study on this. Make it a little link here. The mere presence of your smartphone reduces brain power. So if you have your phone on your desk right now, you are reducing your brain power. Like even if it's sitting there, face up, face down, doesn't matter, it actually distracts your brain, okay? So they've done a study with 800 smartphone users. They did an experiment where they had students participate in something that used their logical, brain processes and their cognitive capacity. And they either had their smartphone on the desk face down, or in their pocket or personal bag, or in another room altogether. Okay? The researchers found that the participants with their phones in another room altogether significantly outperformed those with their phones on their desk. They also slightly outperformed those with their phones in their bag. Okay? So you aren't always going to be able to have another room to put your phone in. Like right now, that might be awkward. Because where else are you going to go put it? You can't leave it in the hallway lying around. That's not practical. But if you put it in your bag or in your pocket so it is out of your visual range, it stops you from being distracted by it. Your conscious mind is not thinking about your cell phone, but your subconscious mind is thinking, ooh, cell phone, ooh, things, I wonder what's on there. Oh, you should check it. Because that's how addiction works, right? Like we're all, I'm working on my computer and all of a sudden I find like I'm on Facebook because I'm old. That's what I do, okay? And I'm like, why am I on Facebook? I shouldn't be on Facebook. I should be working, right? But all of a sudden there I am because it's right in front of me. And so the same thing goes for the phone. Yes, Jim? Oh, it says it was a series of tests that required full concentration in order to score well. So something that required concentration. So basically what they're saying is that your phone takes away your concentration because you actually have to tell your brain to stop thinking about your phone so you can focus on your work, right? So you're using a part of you're not consciously doing that, but subconsciously you're thinking, okay, work, not okay, phone. So anywho, that was one of them. And next day I will show you the ones on the Pomodoro technique. Yes? You have a question? I will be over in just a moment. Okay. Yes, oh yes, this one is correct. Yes, like that one, exactly. Yeah, yeah. Sorry, you gotta put 1, 2, 3. Okay. Will that mean whether it's -2 or not -2? Yeah. It only matters when you're doing quantity. Yeah. Yes. The only thing that doesn't matter is okay, how we get up here? Yeah. 3 and 4. Wow. Okay, so we're going to be going. Yeah. So we're going to be doing 4.
I reached like one trillion.
If you are done, I will put the homework back up there so you can know what it is, where to go. There we go. Oh, I didn't write it. Oh, yeah. Sorry. Oh, dear me. Okay. You got math stuff. I need help with math. I cannot help you with that. I'm sorry. Pick up 12 is beyond. I can get up to math 10 and part of math 11, and then pick up 12 on my phone. It was how many years?
You always say like years ago. You don't look like that many years.
I'm 51.
What?
Yeah.
What?
No.
Yeah. Yeah. 51. And it's actually a vacation. It's the most freeing thing ever.
That's not
Yes. Mm-hmm. I actually got this belly and after a little so
that's so cute.
because yeah, it's like you get to a certain point where you're like, I need this people, I'm dressing a certain way. All these things I ain't got no time for no more time for that. It's so good. It is a good place to be. Well, thank you. Well, one thing is I want with the graders, they don't show, right? Yeah. Yeah. am I gonna do? Yeah. Yeah. Oh, okay. So at the macroscopic level, this one is like your brain is exploded, yeah? Okay. So we're gonna be looking for the unit for the solid. Okay. Find the unit of the solid. K is equal to rate over. So we have K is equal to the rate, which is molar per second, over the concentration of A, which is measured in molarity. Molar per second over molarity. Now, and this molarity and this molarity is the same. So what happens to they cancel out the ones on the top and the bottom, and then the left is the one on the top. So the unit is always the same. Oh. That's because units always is for K is equal to C squared. So this should be molar squared. So that's molar squared. And so that'll cancel to be 1 over S over M. Right? Yeah. And so what you'll end up with is then when you divide by something, you divide by something. That just means it's like 1 over S times M. Yeah. I know, right? It makes your brain go lower. Everyone knows you have a quiz on measurement on Thursday. No. Is this measurement? No. So how will you know what is on the quiz? If you go to our team, and you look up upcoming quizzes and tests, it says quiz on making measurements on Thursday, September 22nd, and it gives you a whole list of things. Okay, and I should actually add into there the pages from here that you should do for extra review if you want to. Okay? So, plus what you got back, you know, that little buret rating thing that you got back, the feedback from that will help you get a good mark on your quiz because it shows you, you know, like, oh, I forgot to go one more place than the smallest division, or oh, I forgot to write my units, or oh, I didn't write my formula when I was calculating the difference, right? So those things will help you, okay? Yes. Huh? What?
Henry Brown to the offense, please. Henry Brown to the offense. This is mine for one who was like, I don't know, like 12 years old. Like, how many years ago? 40 years.
He has to do something. What's my water bottle? Is it? I have no idea. Yeah, but I was like, no, no, that's for last week. Yeah, we're jealous. Okay, but anyways, so what if we are sitting like Gerardo here? Sort of in the classroom. I could probably do here. And it says, is she here? I'm like, no, Gerardo. Okay, so it wasn't narrow that down. It's on the
I'm sorry.
You're right. We invite you guys back. You know what I mean? What do you got? I'll know it. All good. Not a big deal. This is another moment. This is another moment. Once again.
Five, four, three, two, one. Are there any homework questions? I don't know either. Since nobody's like yelling anything, I'll assume that's a no. Yes? Sorry. Okay.
I think I left my my textbook in my locker. So
Oh,
can I just
yeah, for sure. To the -2? Okay, so ladies and gentlemen, on page 73, number 2, there is this weird unit, which is grams, centimeters to the -3. Now, if I told you 2 to the -3, could you write that as a positive exponent? What would that be as a positive exponent? 1 over 2 to the 3. So centimeters to the -3 is 1 over centimeters cubed. So if you have grams times centimeters to the -3, you now have grams per centimeter cubed. That is a mass unit. What is centimeters cubed measuring? Volume. And so altogether, this unit is grams per centimeter cubed, and that's a unit for density. Okay? I will throw things in here like this, not like super regularly, but because you will see them in science a lot as you progress through the years. Did that make sense? It isn't. It's exactly the same thing. It's just another way of writing it. Sometimes we will do that, like, especially if you're typing things, it's kind of nice because then you don't need to have like the this over that kind of thing. And it's a fairly standard notation as you get into university. They will tend to use things like that a lot. So I like you seeing it. You don't have to use it, but knowing what it means is a good thing. Exactly the same thing. Those two units are equivalent. Yeah. Anything else? Yes. Number 15 on page 70. And that is 5.4a. Sorry, what number did you say? 15. Okay, so this one. Okay, cool. So we are on page 70. This is number 15. So we have the density. I'm just going to write down all the things that I have because I like to do that. It organizes my thoughts. Density is equal to 22.57 grams per centimeter cubed. We know that we have a 1 kilogram block, so that's mass is equal to 1.00 kilograms. And if I'm looking at this, I'm looking and I'm like, ooh, this is grams, that is kilograms. I probably want those to be the same. So I'm just going to go ahead and say that's 1,000 grams, okay? Just to make my life a little easier. And then we have a rectangular block of osmium. And it is, two dimensions are 4 centimeters and 4 centimeters. And then we want to know, right, so we're 4 centimeters here, we're 4 centimeters up and down, and we want to know how many centimeters that is. Yes? So if I know 2 dimensions of a block, how can I find the third dimension? Because what's the volume of cube equal to? Volume of cube equals length times width times height. It doesn't matter which one I call what, right? So I can just pick one. I'm going to say, let's solve for length. Okay, so I have length is equal to volume over width times height. Yes, and I know that my width and my height are 4 centimeters each. Okay, so now if I know the volume, I can plug it in there because this is going to be 4 centimeters and this is going to be 4 centimeters. Now I need to know the volume. I know my mass, I know my density. Can I find volume? Yes. So we're going to say volume is equal to, I'm going to do it using unit conversion because I like that, 1,000 grams. I'm just going to underline my uncertain digit there because it was 3 sig figs in that number, times, I want to cancel my grams and find centimeters cubed. So we have 22.57 grams and 1 centimeter cubed. So what have I done with my calculator? There it is. 1,000 divided by 22.57 is 44. Oh, 10 battery low. But that's like not the same. Okay. Okay. Oh, okay. That's all right. I have this one. Look at that. Okay, come here. 44.307. There are more digits. It's actually 44.30660, but I'm just keeping an extra couple digits past my sig figs, which would be 3 sig figs. Okay. So I can now plug that in here, and that is centimeters cubed. 44.307 centimeters cubed. What's going to happen is my centimeters and my centimeters will cancel with 2 of those centimeters. So I take that number and divide by 16, and we get 2.769 centimeters, which would then round to 2.77 centimeters. Is good? Cool. So this is like the kind of thing, not this question in particular, because they're not going to ask you that on AP, but they will expect you to take different knowledge from different areas of your life and like combine them together. Like I know density and I know a volume of a rectangle, and put those 2 pieces of knowledge together to like make something happen. Okay? Yes. You actually don't put a line on it at all. You just stop there and round to that digit. Okay? It really doesn't matter when you're just showing it in your work. That's just for my own, like you don't need to write it at all. You don't need to show this line here at all. I'm just keeping track of it for myself, saying that has 3 sig figs. Or I could just not write that, and I could just write 3 sig figs up top, just so in my mind I'm like, that's 3 sig figs, so I'm not going to go to, say, 4 sig figs, right? Yeah, that's all. Algo más, anything else? Okie dokie, are we ready to learn about molar volume? Page 79, 5.4D. Five point four C. Three A, the answer key may be wrong. Okay, you know what I'll do? I will write that down and I will check it for you. Where are we? Okay. Oh yeah, probably. You know what? 3s and 8s, same finger on the keyboard, right? But opposite hands, so that's probably incorrect. So that was page 78, number 3A, typo. Check it. Okay. Oh, there we go. Ladies and gentlemen, what does the term molar mass mean? What does the term molar mass mean? It is the mass of 1 mole of a substance. And it is measured in grams per mole. Yes? What do you think molar volume means? Volume of 1 mole of a substance. Okay, so if you have the volume of 1 mole of the substance and its unit would be, you know, liters per mole, or if it's something that's more compact, like for gases, it's usually going to be liters per mole, but for solids and liquids, it could often be milliliters per mole or cubic centimeters per mole, but it's always going to be per 1 mole. So molar means per mole when it's like at the beginning, when it's an adjective. Molar mass, mass of 1 mole. Molar volume, volume of 1 mole. Now, what does just the word molar on its own mean? Yes? Sorry? They are your teeth. Okay, another meaning. That was good. I like that. Okay, what else? Molar. Concentration in what unit specifically? Okay, capital M means molar, just plain molar, not molar anything, okay? And it means the concentration of a solution in moles per liter. So we've seen the word molar in 3 contexts now, yes? Molar mass, mass of 1 mole. Molar volume, volume of 1 mole. The unit, molar, means the concentration of a solution in moles per liter. So that's the one that's a little bit different, yes? So you'll want to get those 3 terms straight in your head, okay? But look, how easy is that? Do you remember when we were finding the molar mass and we did not know what the substance was? We found our grams and we divided by our moles, and Bob's your uncle. Are you guys familiar with that expression? It just means, and there you go. And Bob's your uncle. It's a weird expression. British. British they've all got all these weird expressions. They pronounce things weird. You guys know Worcester sauce? Worcestershire sauce, which is Worcester sauce. Worcester, or is it Worcestershire sauce? Worcestershire. Anyway, Worcestershire sauce is Worcestershire sauce. Okay. They pronounce all sorts of things really weird. Okay, so for gases, we'll put a little cloud around it like a gas. There is an actual standard molar volume of a gas if we are at standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of pressure. It's called STP. Those are the conditions for STP, 0 degrees Celsius and 1 atmosphere. Do you know what would happen to a gas if we heated it? Yes. It will expand. And if we cool it, it will contract. So the molar volume of a gas changes a lot depending on the temperature. What if I put a gas under pressure? And by putting it under pressure, I mean I squish it. What will happen to its volume? It will get smaller. And what if I lower the pressure? It will expand. So gases don't have a consistent molar volume, it changes depending on the temperature and it changes depending upon the pressure. In the gases unit, we will learn to deal with things other than standard temperature and pressure. But for now, we're just going to deal with this one. And it's actually the same for all gases. Okay? It doesn't matter what gas you have. 1 mole of any gas oxygen gas, methane gas, carbon dioxide gas, nitrogen gas, any kind of gas you could name, if we are at, what's the temperature? 0 degrees Celsius, and what pressure? 1, and what does ATM stand for? Atmosphere, okay? 1 mole of any gas at 0 degrees Celsius and 1 atmosphere will occupy 22.4 liters of space. And if you're like, well, what if the molecules are bigger? And what if the molecules are smaller? Well, here's the thing about gases. Most of the gas, if you've got a volume of gas, what's most of the space taken up by? Just empty space, right? The particles themselves. So let's say we had a gas that had small particles, and that's how much space it took up with 1, 2, 3, 4, 5 particles. It wouldn't matter if you had bigger particles or more massive particles, because they still take up that amount of space because most of the space is empty space. There are slight, tiny differences just depending on the actual size of the particles and also to do with the attractions between the particles. But if these particles are quite far apart, is there going to be much attraction between them? Like, you know, water, if you have a puddle of water on the desk, does it spread out or does it stay together? It does spread out a bit, but does it like just go? No, it stays together in a discrete area, yes? Because water molecules stick to other water molecules. What do we call those forces that hold one water molecule to another water molecule? Sorry? It is surface tension, and it is caused by a particular type of force. Intermolecular forces. And specifically in water, anyone know what it is? Hydrogen bonds. We have our biologist over here. Yes, hydrogen bonding is extremely important in both chemistry and in biology, okay? However, gases are really far apart. And you can think of all attractive forces get smaller the further the distance. So gravitational force. If you were up on the space station and you jumped out into space, would you fall to Earth? No, because the attraction is not great enough to overcome, you know, your movement around the Earth. But if you were a meter from the Earth and you jumped, you would fall to Earth because it's close by. Forces at a distance are stronger when the things are close by. So forces between molecules are stronger when those molecules are close together, like in a liquid or a solid. They are weaker when the particles are far apart, like in a gas, okay? You don't really need to know this right now. Remember, so many things you don't need to know right this second. The deal is, though, that all gases, doesn't matter how big they are or how small they are, they will occupy 22.4 liters of space because most of that space is just empty, okay? So gases expand upon heating. Here's our cold air. Here's our hot air. When the air molecules are heated, hopefully you know that means they move faster. And because they are moving faster, the air molecules then spread apart. And as they spread apart, the volume increases. However, no new molecules have been added. So the mass stays the same, okay? So as temperature increases, the volume increases. And so the molar volume increases. Doesn't matter how many moles you have, whatever it is, it'll also increase. But density, remember, what is density? Density is mass over volume, and the mass stays the same, but the volume does what? Increases. And so if you have a larger number on the bottom, then the density will get lower. Does that make sense? You know, you've got a balloon, right? And it's got, there is gas in here, and if we put it on a balance, it would weigh a certain amount. If we heat it, but everything's still trapped inside, would its mass change? No, because nothing's escaping, but the volume would certainly change, and so the mass would stay the same, the volume would get bigger, and so our density would become less. Is good? Okay. Oh, and we already talked about this, but we're hammering it home here for you. If the pressure is 0 degrees Celsius and 1 atmosphere, if you have CO2 gas, its molar volume is, don't look at the number, what is the number? 22.4, because it's as easy as 2 plus 2 equals 4, okay? And if you have helium gas at STP, 0 degrees and 1 atmosphere, what's its molar volume? 22.4 liters per mole. And if you have 1 mole of chlorine gas at 0 degrees Celsius and 1 atmosphere, what is the volume? 22.4. And what if I gave you 2 moles of oxygen gas? How much volume would it occupy at STP? 44.8, okay? Yeah, very good. Okay. If you increase the temperature, 1 mole of gas will occupy more space. So you'll notice there's another sort of standard temperature and pressure, but it's not, we can't call it standard because we already have one that is called standard. So we have another one that is often used, which is called normal temperature and pressure, okay? You are not responsible for knowing this number, okay, the 24 liters, but what you are responsible for knowing is that if you are at a higher temperature, right, this is higher than 0 degrees, then the molar volume has gotten bigger, larger, okay, because you'll have more volume for the same number of moles. But it will remain the same for all of them. All of them at 20 degrees are now 24 liters, as long as we're keeping the pressure the same and the temperature the same. And this, in fact, led Avogadro, the scientist, to have a hypothesis. And his hypothesis was that equal volumes of all gases at the same temperature and pressure will contain equal numbers of particles. Yes? So if I was to give you 3 identical boxes, and they were all at 57 degrees Celsius and 5 atmospheres pressure. And I told you there were 3 moles of CO2 in this container. How many moles of helium would be in the second container? 3. And you could do the same thing for, say, ammonia. Okay, there would be 3. Okay, and so that's what Avogadro said. He said, as long as you are at the same temperature and the same pressure, and you have the same volume, then the number of moles will be the same. Okay, same. Calculating molar volume, super easy. Just like calculating molar mass, except for instead of mass, you're going to use volume. Okay? Because like we said, the molar volume does not have to be at STP. You could be asked to calculate it at some other temperature, in which case we would have to give you the volume and give you the moles, and you'd have to calculate it from there. Okay? So here we are at 30 degrees Celsius and 1 atmosphere of pressure. So we have 30 degrees Celsius and 1 atmosphere of pressure, so we are not at STP. We know the moles, and we know the volume. And we would like to know the molar volume of oxygen in liters per mole. So pretty straightforward, yes? We would say, okay, I need to plug in my volume on the top and my moles on the bottom. My volume is, well, I'm not given liters, but you guys know how to convert from milliliters to liters. How many places do you move the decimal? 3. So we move our decimal place, 65.4 becomes 0.654. Okay, there we are. You could show the work if you wanted to, but you could just also just move the decimal, and that would be perfectly good. Okay? Did I do something wrong? Huh? Oh, that should not be there. This should be here. No, it should be here. There we go, because it was 65.4. Yes? Because yeah, okay. Missing 0. Okay, so here we go. We've got that. We know our moles. We do the division. Let's see if I actually did the division using the correct number. 0.0654 divided by 0.00263 equals, and I used the 0 when I did the division. I just didn't type it in. Okay, so this is a correct number here. So that is the molar volume of oxygen at 30 degrees Celsius and 1 atmosphere. Is good? That would be your final answer. Done. Now, what if, common mistakes students make. Okay, so these are things I have seen many times over the years. They get everything upside down, right? So instead of doing liters per mole, they do moles per liter, molar volume. Unit is liters per mole. So don't write it upside down, okay? If this happens to you, and you're like, oh, I got liters per mole, Then do the question again, just take everything and flip it upside down, okay? La, 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 there we go. Yay! Okay. What? Oh, I get people trying to convert, right? Because it's like we have done so many conversions, yes? That they try to convert into a molar volume. But remember, the unit is liters per mole. And if you just try to convert this, and you use 22.4 liters per mole, we're not at STP, so number one, that would not be a correct conversion factor, but number two, you're ending up with a unit that is not what you want. Yes? So just watch out for that. People just, like, molar volume just sounds a little confusing sometimes, and people are like, okay, I'm converting things, so I'll just keep converting things. Don't do that. Solve for liters per mole. It'll be straightforward if you do it that way, okay? Molar volume is found by dividing, not by converting. Here is an experiment. Maybe on that one of those long days, because we're gonna have a long day during parent-teacher interview day. We'll have like a 110-minute class. You know that, like, not meet the teacher, that's this week, okay? Meet the teacher, your day is normal, but the one that's a little bit later, like in October, they've made it so it's going to be like long blocks, like morning, afternoon, so you have 100, but we end at 1:30, so, but everything's going to be equal, so it's going to be like 110 minutes each class. Maybe we will actually do this experiment. That would be kind of cool, yes? Because what you do is you take a tube and you have a rubber stopper and it has a hole in it, okay? Can you imagine a rubber stopper with a hole in it? Okay, it looks like from the top down, it looks like this. There's just a hole in the middle, okay? What that does, it allows water, this tube would be filled with water when it starts, okay? So the water would be all the way up to the tippy top, yes? So there's the water at the top. And then what you do is you take a little piece of wire and you insert a piece of magnesium into, like, through the hole in the stopper, yes? This is why we're going to do it, because it's hard to describe, right? It's going to be nice to actually see this in action. And then what this is full of is, I'm sorry, this isn't actually water. This is an HCl solution. So what is the name of that compound there, HCl? Hydrochloric acid, yes. And if I was to give you, this is remembering from grade 10, if I was to give you, we have now have magnesium, and we have hydrochloric acid. What's the state for magnesium? Solid. And what's the state for HCl? It's aqueous. Could you predict the products? Try it. See if you can predict the products. You might need to remember what your types of reactions are. Oh, gave away the answer there. So who is going to replace whom? What do you end up with? So who is booting out the other guy? Who's doing the replacing? Magnesium. Okay, so magnesium is doing the replacing. Who is it going to replace? Hydrogen, because remember, when you have hydrogen at the beginning of a compound, it kind of behaves like a metal. Yes, and so you actually have H plus and you have Cl minus. And now I'm going to tell you that acids are still molecular compounds, even though they're made of ions, which makes me unhappy also. Okay, we will talk more about that in grade 12. It will make a lot more sense. It's because some acids like HCl, when they're dissolved in water, they actually split apart completely into H plus and Cl minus, but most acids don't do that. Most acids just stay holding hands with their little partner, and only a very little bit actually comes apart into ions. Okay? You can just pretend I said nothing if that went over your head. Okay? You can be like, I'll wait till grade 12. Thank you. Yes?
So is H plus the reason why it's really important to make sure we have the positive and negative?
One of the reasons, yes. Yes. Okay, so for ions, it is really going to make a big difference whether you have the positives and negatives. And it will make a huge difference when we start doing ionic equations where we take out the ions that aren't actually reacting. Yeah, hugely important. Okay, so now we have Mg, and it's going to boot out the hydrogen. Now, what compound will you get when the magnesium gets together with the chloride? What is its formula? MgCl2, because magnesium is in column number 2, so its charge is plus 2. Chloride is in group 17, it's 1 from the end, so it would be minus 1. Okay, so that's MgCl2. And who is our other product? H2. And if I had to put my states on these things, what do you think they would be? MgCl2, and you will actually get a chart that predicts whether ionic compounds are going to be aqueous or solid. We'll look at that later, but that's going to be aqueous, and that's going to be a gas. Okay? So, in here, we start with the acid all the way up at the top, and then we take this plug that has the stopper that has the magnesium sticking through it, and we slot it up and in. So now the magnesium is in contact with the hydrochloric acid solution, and the two can start reacting. So what are these bubbles? What kind of gas? H2 gas. So up here, this reaction's been going on for a while. Up here we have the collected H2 gas. Yes? And if we had little markings on here, could we measure how much gas was collected? Yes, if there's markings on there, yes, you could. Okay. So this would be like, 1 milliliter, 2 milliliters. It would actually have like little gradations on it, okay? Often we will even use a graduated cylinder and just turn it upside down, okay? Huh? Oh, because it's closed. I'm sorry, that's a closed container. That makes a huge difference. This is like you take the graduated cylinder and you turn it upside down so it's glass on the top. Good question. I didn't realize the picture was so ambiguous, but it really is, okay? Yeah, so this is where you could actually find how much H2 is made. Okay, you could find the volume, and by knowing the molar volume, you could actually calculate how many moles you have at that point. Okay, so here is a gas collection method. It describes how it's made down here. Here is some data we could get from this experiment. So somehow or other, we know that we have collected 0.0183 moles. My guess is that, I don't know how they did that. That's a good question. We'll do it a little differently, so we'll actually get something. Maybe they did mass. Oh, I know. They would have done it until all the magnesium is gone, and then they would have figured out the ratio between magnesium and hydrogen. Because what did I forget to do in my equation? I forgot to balance it. So I would need a 2 there. Anything else? We're good. So what you would do is you would actually react this until all the magnesium is gone. Yes? Let's say you started with 5 grams of magnesium. Yes? This is like going into 3 units from now, okay? You could find the moles of magnesium that were reacted, yes? For every 1 mole of magnesium that reacts, how many moles of hydrogen do you get? 1. Because it's a 1-to-1 ratio. 1 magnesium makes 1 H2. Yes? Don't worry about it if you're kind of like, huh? Because that's 3 units from now. But that is how they would figure out then the moles of hydrogen. They're not just magically counting the atoms. Okay? So here's the data. You have a room temperature and room pressure. Calculate the molar volume. Why don't you guys cover up the solution and see if you can do it? So put a piece of paper over top of the solution and see if you can calculate the molar volume of H2 at 21 degrees Celsius and 0.991 atmospheres using the above data. And if you don't have any blank paper, there's some blank paper in that little bin at the back there. Yes, of course. You're calculating, you're doing this problem. I know I said cover it up. It's okay. Cover it up. It's all right. You can see the answer there. It's basically, so can we just skip past that now? We're good? Okay. Alrighty, good. All right. Here we have solids and liquids. Now solids and liquids, what's different about solids and liquids from gases? They are not very compressible. They do not change volume a lot when you heat them or cool them. They do a little bit, but not very much. So each solid and liquid has a different molar volume. The volume will depend on how closely the particles are packed, and there are different ways that particles pack depending upon the type of particle. Okay, and you're not going to know that until you take first year university, because it's not part of the AP curriculum. Okay, but particles, for example, could be packed like they are in A, where all the little atoms are stacked one on top of the other. Okay, this would be a 3-dimensional structure, but we're representing it in 2D. Or they could be packed like they are in B, where they're sort of like fitting in those little gaps. Consider those two solids. Assuming that A and B have the same mass, which packing arrangement would have larger volume? A or B? A, why? There's more space, yes? Which packing arrangement would have the larger density? B. Okay, so as molar volume increases, or sorry, decreases or increases, density decreases, and vice versa. You could write it the other way as well. Not significantly compressible. We talked about that. Here's just a little picture showing you, right? Here's our gas. And we've got a container with like a piston on the top, and we push down on it, and the particles just become closer together. But there's still lots of space between them. Look how much it moves when you try to squash a liquid. Not really, okay? So the gas, you can compress it quite a lot. A liquid you can compress hardly at all. And a solid, not really. Yes? It's just how it's putting pressure behind it, so it just squirts out faster. I don't know. Like, you're forcing it. Yeah. Yeah. Like, here's the thing, is that it is under pressure. It's not getting smaller. You provided an opening, it squirts out. So it can be under pressure, but it would get smaller if it could, but it can't, so instead it gets squirted out. Yes? Yes. Solids and liquids do expand upon heating, but the amount of expansion is small compared to how much gases expand. Does molar volume increase or decrease upon heating? Molar volume increases, yes. So what happens to the density when you heat it? The density decreases. So once again, we have found that as molar volume increases, the density decreases, and vice versa. Molar volume can be found from density and vice versa, because here you have mass over volume, yes. Mass can be converted into moles, yes. So then you would have moles over volume, and then what would you do to that to get the molar volume? Flip it. And the same thing the other way around, yes? If I give you density, you can say, or sorry, if I give you molar volume, you could convert moles into grams, and then you could take the whole thing and you could flip it, all right? So there's several ways of showing the work. You could do it that way. You could do your conversion in situ, like just right there. But if we were to say, what is the molar volume of iodine? Its density is 4.94 grams per centimeter cubed. So the density is 4.94 grams per centimeter cubed, and that's the density of iodine. What do we know about iodine? Iodine is diatomic, so the density of I2. And we want to find the molar volume. What is the unit of molar volume? Liters per mole, or because this is a solid, because iodine is a solid at room temperature, we could also say or centimeters cubed per mole, and that would be fine because you have a volume unit and you have a mole unit. So what I would do, if it were me, I would probably say molar volume, and I would start with this number, but I would write it upside down to start with. Yes, because I want my centimeters cubed on the top. Yes. Actually, you should know a few of them, okay? So you should know that all of your metals are solid, except for mercury, okay? And you should know that all of the noble gases are gases, okay? If I said nitrogen, would you know that's a gas? Yes. Oxygen, would you know that's a gas? Yes. Gas, liquid, solid. Your halogens. Fluorine and chlorine are gases. Bromine is a liquid, and iodine is a solid. What would you say is happening to the intermolecular forces as you change from one substance to another, going down this column? What would you say about the intermolecular forces between iodine particles as compared to, say, fluorine particles? They are higher. Yes.
Why does that not happen?
Because these ones, they're just, I mean, this one will have a lower melting point. Okay, because this one is diatomic, it actually has 106 electrons in it. Okay, bromine has 70 electrons in it, and it turns out it is those numbers of electrons that are important in determining whether it's going to have strong intermolecular forces or not, and we'll look at that another day, okay? Whereas these guys, because they're not diatomic, xenon has only 54 electrons, and I'm not sure about radon. It's radioactive, and there we are. Okay, so my molar volume, I want to find centimeters cubed per mole. So I'm going to take this and I'm going to write it as centimeters cubed per 4.94 grams. Good? I can do that because that's the way around I want it. And what do I now have to do with my grams? Because I don't want grams, I want to have moles. Where do I want the moles? I want them on the bottom. And where do I need my grams to be in order to get rid of them? On the top. So what is that conversion where I have grams per mole? That is my molar mass, which for iodine is going to be 126.9 times 2. 253.8 grams per mole. And you can see we're going to now end up with centimeters cubed per mole, and that's going to be 250 divided by 4.94 equals 51.4, because I have 3 sig figs, 51.37, okay, centimeters cubed per mole. Or you could do it in milliliters per mole. Okay? Yes? Uh-huh. Oh. Times 2. Doesn't it? Oh, and that's not 129.9. It's something else. Oh. Thank you. All right. One last question, and then you can go home and do the exercises on this one. So what if we wanted to find the density of propane propanone? Now, do you guys know what the prefix prop means? Prop means 3, okay? It goes meth means 1 carbon. What means 2 carbons? F, 2 carbons. Prop is 3. And bute is 4. And then after that, it's like penta, hexa, hepta, you know, like the normal prefixes kind of thing, right? Those first four, I had a student one year come up with this mnemonic device, me eat peanut butter, okay? But if you're allergic to peanuts, you might eat pita bread instead. Okay? Otherwise, you go into anaphylactic shock. Propanone looks like this. Whenever you see the ending "one," it means you have a double bonded O somewhere in the middle of a carbon chain. Okay? No. There's actually no organic chemistry specifically on the AP exam at all. Okay? So when I mention these things, it's because, you know, when you go to university, there might be organic chemistry in your first year, so it'll be nice to have seen it before. And you had a question, yes? Aaron. Not a whole lot, because we got so much else to do. You get to learn it in bio to a certain extent, and we will bring a little bit of it in the reaction section, because we'll be doing reactions of hydrocarbons, and we'll be doing reactions of organic acids. Yes? Yes. Now is fine. Okay. Yes. Oh, and the answer key. I'm shocked. Anyway, go ahead. Yes. Three A. Yeah. Oh. Yes. Uh-huh. It being me. Okay, so in other words, 3A is a hot mess, and I need to fix it. Okay, answer is 10.2. Do you feel like you want me to go through the example of the density of propanone, or do you feel like you can just go on your own? I'm happy to do it. I'll do the example. If you want to leave, you can leave, but don't make any noise because people will be listening. Yes? So we're going to do the propanone example. Molar volume of propanone is 58.63 milliliters per mole, and we want to know the density. And density would be in grams per, what would you like? I would personally choose milliliters because I've got milliliters there, yes? So I am solving for my density. How many grams per liter? And I want to start with this number, or sorry, per milliliter, sorry. How would I write this number, right side up or upside down? Upside down because I want to have the milliliters on the bottom. Yes, so I'm going to take that number and flip it so my milliliters start on the bottom. So we have 1 mole per 58.63 milliliters. I want milliliters on the bottom, so that's good, but I don't want moles on the top, so I need to cancel with moles on the bottom and grams on the top. And propanone, you are given the formula CH3OCH3, you would calculate the mass, which is 46. 0.0 grams per 1 mole. Moles cancel, and you get 0.785 grams per, and the only units you have left are grams and milliliters. Okay, so you can do pages 85, 86 for homework. Okay? Yep. Howdy.
Let me answer this one.
Yeah.
Is this for like anything that's in the state of gas?
Yes.
So like, it wouldn't matter if it's like hydrogen molecules.
Hydrogen molecules, helium atoms, methane molecules, as long as it's in the form of gas and it's at that temperature and pressure, that's its volume. Yeah. Howdy.
Oh, can I take the read quiz?
Yes, do you want to do it when?
Tomorrow, like?
Yeah, absolutely. Hi.
Would I retake quiz? When can I do it?
You can do it anytime you like. Do you want to do it tomorrow, Flex? Cool. Let's do it. Anyone who wants to retake their quiz, flex time's good. Let me know if that doesn't work for you and we might be able to work something else out. Question 5. Okay, let me write that down.
Yeah. 25.9 or question 5?
Question 5.
I just wanted to ask you, do you usually teach like AP Chem?
Yes.
Okay.
Well, I teach it, Ms. Wu and I alternate years.
Okay.
So what will happen is if I teach you this year, I will be teaching AP Chem next year.
Oh, so you get the same kids.
So I get the same people because,
That
you know,
helps.
that
Yeah.
way if you've taught certain topics,
Then
you
what
know
to
which ones
decide.
you've
Oh,
taught.
that's
Yeah,
smart.
yeah,
Okay,
yeah. Howdy. In AP Chemistry, it is essentially all the same stuff that is in regular Chemistry 12. There's actually a really big overlap between the two courses. Okay, so there are 6 units in Chemistry 12. Unit 1, we add some extra stuff. Okay, so reaction rates is a Chemistry 12 unit. We add in things like drawing graphs with it and doing a bit of more math with it. Okay, in section 2, which is equilibrium, so it's looking at reactions that go both ways. So we do all the regular stuff, and then we would do some more stuff with like thermodynamics, which is looking at how temperature affects the position of an equilibrium. When we look, again, we add in the math component. In regular Chem 12, we just sort of look at it like, oh, you know, the equilibrium shifts one way or the other. In this one, we're actually quantifying it.
So it's going to be like
More in depth. It's a lot more in depth. And that's the biggest difference between the two. We actually do most of like the extra stuff in grade 11. So there's not as much extra stuff in grade 12 because grade 12 in itself is like, if you take regular Chem 11, Chem 12 seems really, really hard for a lot of people. Okay. Not for everybody, but for some people, it seems like a big step up. If you've taken 11 enriched, Chemistry 12 will probably seem easier actually than Chemistry 11 enriched because this year we're doing a lot of the university stuff already.
Okay.
So yeah.
For an AP, would you be skipping like the first year of university or something?
If you get a 5 on your exam, yes.
Okay.
Sometimes if you get a 4, it depends on the university.
I see it.
Yeah, you don't have to skip it unless you go to McGill. McGill requires you to take the credit, but everybody else is like, no, if you want to retake it in first year, that's fine. And a lot of people choose to do that because university is like a kick in the teeth, and it's kind of nice to have a course where you're like, I know I can get a good grade in this because I've already done it once, and things that didn't make sense the first time are going to make sense the second time.
Okay.
So yeah, so whatever you choose to do with it is your option. Yeah,
Great, thank you.
yeah, you're welcome. Hi.
I was wondering on a question where there's like formula units I have to put in, right?
Yeah.
I lose 0.5 if I don't put that in, right?
It depends on the context.
Okay, because for me, I lost 0.5 on, because, okay, the only reason why I didn't write it wasn't because I forgot, it was because I have no space to write it. So I lost 0.5 for that.
Okay.
And
Can
then,
I see the question? Because I want to know why I specifically decided that. Oh, yeah. You can't have like no. You can't have a number with no.
so I just ran out of space and I was like, okay.
You can always put a little thing.
Hey, I'll do that tomorrow.
Yeah.
And is there a maximum amount I can do, or can I do 4? Just like, if, let's say like I forgot, like another unit.
No.
Just 0.5.
It's probably like 25, show your units.
Okay, so like that's
Yeah. Yeah.
Thank you.